Okay. So can anyone confirm if you are seeing the slides?
Yes, sir.
Sige. So this afternoon, we will be relating the properties of compounds to the intra and intermolecular forces of attraction between them, okay, between their atoms and between their molecules. Okay, so our learning targets is for us to explain the chemical and physical properties of compounds and then distinguish the types of intermolecular forces present and then relate molecular polarity and intermolecular forces of attraction to COVID-19. So I'll just be giving snapshots of examples, but or giving out hints, but it's actually for you to do in your performance task. Okay. So first, let us have the first learning target. Out of the many compounds that we have, out of the many chemical formulas, chemical names and sources, okay, it is also important to know their different uses, okay, different uses, their benefits or the harm that they can bring, okay, their different physical and chemical properties. So when you talk about these compounds, whether they are ionic, okay, or covalent. Okay, for example, quicklime, CaO, or covalent carbon dioxide, Cl2, Cf2, which is freon, found in air cooling devices. So they can have their own properties, and we can trace those properties back to their the interactions between their atoms and in their molecules, interactions between their molecules. All right. So let's deal first with properties of ionic compounds. So there's actually an experiment before this. That's why it jumped directly. But let's have the experiment lang tomorrow. So for ionic compounds, you'll know that they have high melting points and boiling points. Okay, they are generally solids at room temperature. Okay, crystalline solids at room temperature. They are hard but brittle solids. So when you say brittle, they can easily be broken down. Okay, and then they conduct electricity as liquids, okay, but not as solids. That means that if you melt you melt ionic compounds, then they will be able to conduct electricity. Okay, so take a look at the melting points and boiling points of selected ionic compounds. Our benchmark here is that of water, which is 100 degrees Celsius. Okay, if you've noticed, the melting points and the boiling points are way past 100 degrees Celsius. So that means it must take a lot of energy and a lot of heat before these substances melt, okay, or before these substances change from solid to liquid in case of melting, and from liquid to gas in the case of boiling. All right. So they have very high melting points and boiling points, and that can be related to their structure, the attraction between the compounds as present in the bonds. Okay. So in terms uh, of brittleness, okay, or their ability to be broken down, then we have the electrostatic forces, okay, between them. So you know that ionic compounds arrange themselves in such a way that there will be an orderly array of negative and positive ions. So each each positive ion will be surrounded by a negatively charged an ion. Okay, so it's an alternating positive and negative charge. Okay, so this is just a two-dimensional view, but you can visualize what happens if you have a 3D. So each negative ion or each an ion is surrounded by a cation. Okay, so if you have this orderly arrangement and you introduce a force, an external force, okay, and if that force is enough to displace your ions, such as this one, okay, what actually happens here if like charges will be aligned or will be adjacent to each other, then there will be a repulsive force between them. All right, so what's happening here? you introduce a force that displaces, okay, some of the ions. So if like charges align with each other, that's the time your crystal breaks or the crystal cracks. Okay, so this is in terms of ionic compounds. That is what makes ionic compounds brittle. Okay, that is why also you might have noticed that there is rock salt, rock table salt, which is a coarser kind of salt, and there is iodized salt, which is finer. Okay, so that means you can have finer salt if you crack them or if you ground them piece by piece, and this is what happens uh, at the molecular level. Okay, so once you break it, you align the like charges, and then the like charges repel each other. All right. In terms of electrical conductivity or electrical conductance and ion mobility, so if you have this set up, okay, the conductivity set up, and you use a solid ionic compound, then nothing will happen to the light bulb. However, if you use either a molten, for example, molten table salt or a table salt in water, you'll find out that the electricity will be conducted, and the evidence for that will be a lit light bulb. Okay, I hope you have done this in junior high, the conductivity apparatus. Did you? For those who have been with us in grade 9, electrolyte, non-electrolytes, you didn't?
Familiar, sir.
The setup ba that you have to dip two prongs and then you try to check whether the light bulb lights up?
I don't think so, sir.
I'm not sure either.
Okay. Okay, so you'll have it in the virtual lab tomorrow. Okay. Sige, ano na lang, you'll have it in virtual lab. Okay. Now, in terms of the properties of covalent compounds, or covalent compounds are generally given the term molecules. Okay, so they have low melting points and low boiling points. Okay, they are mostly liquids or gases at room temperature, and they are mostly nonpolar. Okay, that means they have limited solubility in water, or even they are insoluble at all. All right, and then they cannot conduct electricity, so the opposite of ionic compounds. So what happens here? In studying the properties of covalent compounds, we look at the bonding between the atoms, okay, the bonding forces within the molecules, and the forces between the molecules. Okay, so this is now we have to look at it both ways. There are forces within the molecule, that means the bond between atoms, and the forces of attraction between molecules. So if you have a single molecule here, it is kind of attracted to this other molecule. And what is that attraction? So that will be our next topic, the IMF. All right. But here is a summary of the properties of molecules and ionic compounds. So you see here that they are opposite to each other, okay? So ionic compounds are mostly crystalline solids, while covalent compounds or molecules are gases or liquids or low melting solids. So meaning, think of butter, so they easily get melted. And then in terms of polarity, okay, low polarity for molecules and high polarity for ionic compounds because they have positive and negative poles or negative charges. Okay, so in terms of solubility, only few or limited solubility in water, while ionic compounds are mostly water soluble. Okay, and then you know how already they are formed. Conductivity was discussed a while ago. So ionic compounds conduct electricity when molten or dissolved in water. Okay? And this will be, you will experience this more once you have your virtual lab tomorrow, right? Boiling. Now take note that melting point and boiling point cannot be explained directly through the type of bonding. We must consider the attractions between the molecules themselves. All right. So that's why we now go to the intermolecular forces of attraction. Okay, the IMF. Right. So when you say intermolecular forces of attraction, these are interactions between molecules. Okay, so the ones we said before, ionic bonding, covalent bonding, these are interactions between atoms, okay, in a molecule or in a compound. Okay, so it's between atoms. Now this time, when we say intermolecular attractions, so this is now between separate molecules or separate compounds, right? So IMF or intermolecular attractions are much weaker than chemical bonding within molecules. So they are different things, all right? And then chemical bonds, whether ionic or covalent, determine the chemical properties because the bonds, it is in the bonds that energy is present, okay? And energy has something to do now with the reactivity, right? The electronegativity and so on, okay? Now, intermolecular bonds determine physical properties. So for example, the density, the melting point and the boiling point, the solubility and the vapor pressure. So all these or most of these are discussed in the handout on 1.5. You can also have viscosity. Okay. Uh, what else? You have there the vapor pressure. And then there are a lot of other properties, especially for liquids. Okay. So if you want, I'll be resending the links later, as well as a supplementary video for COVID. Okay. There are three general types of intermolecular attractions or IMF. First one is the dipole-dipole attractions, or we just say dipole-dipole. Second is hydrogen bond, which is practically a dipole-dipole interaction. It's just a special case, okay? And you'll know why later. And then you have London dispersion forces. So in some textbooks, you can just say they just say London forces or dispersion forces. Okay? In some textbooks, you can also have LDF, okay, or LDF, London dispersion forces, right? So here is a table detailing the kinds of attraction. Okay, so you notice that they are classified as intramolecular, meaning inside the molecule or the compound. So this is where chemical bonding is. So ionic, covalent, metallic. And you have now intermolecular forces of attraction. So you can have dipole, ion dipole, which is an extension of the dipole-dipole. Okay, you also have hydrogen bond or ion-induced dipole, dipole-induced dipole. So for now, we will be focusing on dipole-dipole and hydrogen bond. The rest will become easy if you know the principle behind dispersion forces, okay, or the London dispersion forces. All right. So again, there are two types of attraction: intramolecular, which are basically your chemical bonds, and intermolecular, which is the attraction in between molecules or compounds. Right. So let's deal first with dipole-dipole interactions. So here we have hydrogen chloride or HCl. So we know that HCl is very electronegative, and then it draws the electrons of hydrogen to itself. So you have here a certain dipole, a certain unequal distribution of charge. So in this example, the hydrogen end becomes partially positive and the chlorine end becomes partially negative. All right. Now, in this molecule also, the hydrogen end becomes partially positive, and this is partially negative. Okay. Now, if you place these two molecules together, there is a weaker interaction compared to the covalent bond. the interaction between the partially positive hydrogen atom and the partially negative chlorine atom. Okay, and we call this, since this is an interaction between dipoles, we call this our dipole-dipole interaction. Okay, dipole to dipole interaction, wherein one dipole is attracted to another because of the presence of partial charges. So dipole-dipole interactions happen in polar molecules. Okay, polar molecules, and if it's very or it the kind of state that you will have depends on the arrangement of your dipoles. So if you have a very orderly arrangement of dipoles, then you can have a solid state. But if the molecules are more random, okay, and there are still dipoles existing in those molecules, so there is a dipole-dipole interaction, then most probably your substance will be in a liquid phase. All right. So for example, think about uh, a certain molecule. What for you think of, this is an analogy, for example, butter. Okay, so in butter there is an orderly arrangement of molecules, that's why it exists as solids, so the interactions are being stabilized. However, if you heat it up, you randomize the molecules of that material, or of butter, so that's why it becomes a liquid. Okay, yeah, that's for dipole-dipole interactions. Now, dipoles are mostly for polar molecules. So remember that in terms of molecular geometry, okay, you can actually get the net dipole moment for polar molecules. So molecules with polar bonds and asymmetric distribution of charge. Uh, what determines if a bond is nonpolar, polar, or ionic? Who can remember?
Is it electronegativity difference?
Okay, very good. So the electronegativity difference between the two participating atoms. All right. Now, what determines if a molecule with polar bonds is polar or nonpolar? So for example, you have a molecule all with polar bonds, but then you notice that the polar bonds cancel each other out. So what was responsible for that cancellation? Why did it become nonpolar even if it has polar bonds?
The dipole moment, sir.
What about the dipole moments, Franz?
Like their net dipole is will cancel each other out, resulting to
Oh,
a zero.
yes, very good. So the dipoles will cancel each other out because of this one, the shape of the molecule. Very good one. And Kyla, arrangement, the way they are facing. Okay, so the shape of the molecule, or the molecular shape or geometry, actually affects. All right. So you notice in the previous discussions, we were talking about the net molecular dipole. Okay, the net molecular dipole. If you have a net molecular dipole, then that means it can interact with other molecules in a dipole to dipole manner, right? The way they are facing, correct? Okay. Now, the dipole-dipole attraction is much weaker than covalent bonds. Okay, and it is important in maintaining the shape of many biological molecules, such as proteins, carbohydrates, lipids or fats, and then the nucleic acids. All right. So these are your biomolecules, or the macromolecules present in the human body. So we are now slowly focusing our discussion into the applications for IMF. Okay, and then we'll see why later. Okay, why is dipole-dipole interaction? Why are IMFs relevant? Right. So the next type of IMF is hydrogen bond, which still falls under dipole-dipole interaction. Okay, so it's still a dipole-dipole IMF. However, the thing here is that a hydrogen is participating. Okay, so this is one distinguishing feature. So it's found in HF and molecules containing OH or NH bonds. So as long as you find these elements, fluorine, oxygen, nitrogen, and you have here a hydrogen that is bonding, okay, that is attracted to those electronegative atoms. Okay, this is a special case lang as their electronegativity and their sizes, okay, affect their hydrogen bonds. So far we only have fluorine, oxygen, and nitrogen that are presumed to be participating in hydrogen bonds. All right. So the strength is 5 times uh, higher than the typical dipole-dipole bond. So it is stronger than the ordinary dipole-dipole, and it is approximately 5% the strength of a covalent bond. Okay, and this is where the importance in biological molecules comes in, because okay, here because it is found in DNA and proteins. Okay, so uh, again, hydrogen bonding exists between these. Wait, between these atoms. So you see that a hydrogen is bonded to either oxygen or nitrogen and fluorine. Okay, so there is a net dipole here, positive. Okay, net dipole, which is positive, and then net dipole. Now take note that these have electron pairs. Okay, there is an electron cloud there. They have 3 electron pairs. So what it does is that the electron cloud gets attracted to the positively charged or the partially positive end, which is hydrogen. All right. So there is another electron pair here. Okay, so it gets attracted. The blue dotted line represents the hydrogen bonding between this hydrogen and the atom. Okay, same thing here, because if you notice, there should be 2 electrons, a pair of electrons there, which can also be attracted to the H plus or the partially positive H, right? So for example, in ethanol, so ethanol is made up of 2 carbons, all the rest with hydrogen, but instead of a hydrogen here, you have an OH group, a hydroxyl group. So meaning you have a hydrogen that is connected to an oxygen here, and then what happens is that this one is partially positive, this is partially negative, and this will get affected or attracted to the partially negative oxygen of another ethanol molecule. Okay, so there is an existing hydrogen bond between them. All right, so that only works for oxygen, fluorine, and nitrogen. Okay, now, where we have been mentioning DNA and proteins a while ago, I hope you have encountered these guys here. So adenine, thymine, guanine, and cytosine. Okay, these in terms of their attraction. Okay, for example, we say that adenine binds with thymine. Okay, this happens in remember the replication, the translation, and that. So the attraction is because of the hydrogen bonds in between them, okay, for DNA and RNA. Okay, so hydrogen is attracted to the oxygen atom, nitrogen is attracted to the H. Okay, and then same thing here, there are hydrogen bonds in DNA and RNA. All right, here. So there is covalent bonding and H bonding in the structure of DNA. Okay, so you notice NH bonds being attracted to O, to oxygen, and then that will stabilize the structure, okay, and paving way to the DNA helix. All right. So these pink lines here are actually hydrogen bonded, uh, hydrogen bonding in action, right? And then another macromolecule is in terms of proteins. So when you say proteins, these are very large molecules with a lot of folding within them. Okay, so there's a lot of folding, and their specific folding uh, is what as an important consideration in determining their characteristics. Okay, so for each protein molecule, you must have a specific type of folding for it to be functional. All right. So in here we are having the helix as well for protein. So you can have this particular type of arrangement. Okay, and you notice that there are hydrogen bonds between oxygen and some carbonyl groups. Okay, so again, hydrogen bonding exists to stabilize the structure of the protein. Okay, here are some forces that stabilize the structure of proteins, and we see that hydrogen bonding is one of them. Okay, so OH and then to O in here. There are actually others, for example, hydrophobic interactions, meaning to say the nonpolar parts of the molecule will clump together. Okay, they will be attracted together because they want to stay away from polar substances or polar parts as much as possible. And since like dissolve like, so they will be stable with each other. So this is what we mean by hydrophobic interactions, right? And we can also have electrostatic attraction. So this time it is ions and COO. Okay, but the main point here is part of the tertiary structure of proteins. Okay, there is hydrogen bonding present. Okay, this is hemoglobin, responsible for oxygenating and deoxygenating the blood. Okay, and then hydrogen bonding is also responsible for the expansion of water when it freezes. So once you take out enough energy, you lower the temperature such that the water molecules will be clumping together and will arrange themselves. This type of arrangement, okay, this uh, this type of arrangement is used to stabilize or to have the maximum effects of hydrogen bonding. So if you've noticed, oxygen here gets attracted to a number of hydrogen atoms. So one, okay, and then two, and then three, okay. So mostly three or four atoms. So one, two, three, and then four. So each oxygen atom will be attracted to uh, a hydrogen atom. So take a look at this one. One, this is two, three, four. And then you notice that there is a gap in between the molecules. Okay, so it has an effect on uh, the density of water once it is frozen or once it is in liquid form. All right. So again, the properties rely on how the atoms or how the molecules are interacting with each other. Okay. As for this case, you have this particular arrangement to maximize the hydrogen bonding between O and the H atoms. Okay. And in doing so, you find out this type of structure. Okay. And it makes frozen water less dense than liquid water. Okay. That's why ice floats. Okay. Again, IMF. All right. Which of the following molecules display hydrogen bonding? Give me one. Hello. Still with me?
Yes, sir.
Okay. Was I choppy a while ago?
No man.
Not for me, sir.
Okay. Please, kuan mi ha, notify me right away in whatever way you can. Okay, I might keep on talking here and then wala na
Mm.
day.
Kyla answered methyl, sir.
Ha?
Kyla answered methyl.
Okay, methyl alcohol. That's one. Very good. Very good, Kyla. So you notice that there is an OH group here. So if you have more molecules of methyl alcohol, then you expect them to have you have hydrogen bonding. What else? Remember the participating elements. So you can also have HF, okay, hydrogen fluoride, and hydrogen peroxide, HO. Okay, again, FON. Okay. Now, the third type of attraction, the third type of IMF is the London forces or the London dispersion forces. These are attractions between temporary dipoles. And what are temporary dipoles, sir? So, for example, you have these two helium atoms, okay? These two helium atoms, if you place them close enough together, then the electron cloud, the two electrons of helium atom number two, will be attracted by the positively charged nucleus of helium atom number one. Okay, in so doing, because of the random movement of electrons, okay, it can happen that the electrons will be found more on one side than on the other. Okay, and because of this attraction, so there is some kind of an electrostatic attraction between them, the nucleus of helium atom number one and the electron cloud of helium number two. Okay, so this is not permanent, it is only momentary or instantaneous, okay, at a particular instant lang. So if this happens, if the electrons move here, there will be there will be a richer area where electrons are found. So this is partially negative, okay, and the one that is electron deficient is partially positive. All right, and then what happens here is that once they get attracted, then the electron cloud of this atom tends to move far away. Okay, so they will be moving to another area. So that's why this is partially negative. And this end here, this end, so it becomes kind of distorted. Ba? This end becomes partially positive. Okay, so this is now a weak interaction. Okay, only a weak interaction. In a matter of time, the electrons can go back to where they're supposed to. All right, but if there are too many electrons or too many helium atoms, then they can also affect one another. Okay, they can induce those temporary dipoles, meaning they can encourage those temporary dipoles to also happen. All right. So when you talk of London dispersion forces, they exist actually in all molecules. Okay. So imagine there is a big molecule here, and then the electrons are moving. Okay, are moving randomly. So there will come a time that one area will be more negatively charged than the other. So for example, if you have this long chain of molecules in here, and then electrons are moving around, and then it so happened that at a particular point in time it becomes more electron rich in this area. So this is partially negative for a moment, partially positive for a moment. Okay, if it meets another molecule that has an opposite charge and they get together, then it partially positive. Okay, and then this is partially negative, and here, because that's where the electrons are. So there is kind of attraction between the partially positive and the partially negative end. Okay, and we call that our London dispersion force. But once electrons go back, okay, or have not been distorted anymore, they go back to normal, right? So London dispersion forces result from temporary charge imbalances, number one, due to the random movement of electrons. Second is that the nucleus of one atom attracts electrons from a neighboring atom, okay, especially if there is a significant difference in terms of their atomic size or atomic radius. All right. So the more protons you have, the larger your electron cloud will be. Okay, and the more electron protons you have, the more you have the tendency to attract electrons, the electron cloud. Okay, the electrons in one particle repel the electrons in the neighbor and create a short-lived charge imbalance. Again, this is temporary. All right. So in here, this is the how temporary dipoles are induced. So think of these as the one in helium. Okay, there is a temporary dipole here affecting another dipole. If it bumps with another, okay, if it bumps with another molecule, then it may induce another dipole from that other molecule. All right, so making it more positive and more negative. Okay, and then it bumps with others, it bumps. So that's why you can have as many London dispersion forces as you can between the molecules. All right. Now, London dispersion forces mostly for nonpolar molecules. Okay, nonpolar na siya. If it's polar molecules na, then we say dipole-dipole moments. So meaning to say, the IMF, intermolecular forces of attraction between nonpolar molecules, are usually that of LDF, London dispersion forces, right? And then you see here that the bigger your atom is, the bigger your atomic radius is, then the greater your uh, boiling point will be. Okay? The greater your boiling point will be, the one in bold. Okay? Now, the boiling point is affected by the IMF. So if you have stronger IMFs, if you have a stronger IMFs between your molecules, then the harder it is, the more temperature, the more energy it will take to boil your compound. Okay, that's why you have a higher boiling point. Okay, so this is experimental. This has been determined experimentally, and they noticed that as we go down the periodic table, there is an increasing, okay, boiling point, increasing boiling point. Therefore, there is an increasing London dispersion forces. So the question is, why are London forces the greatest in large molecules? Or why are London forces increasing as the size of the molecules increases?
More electrons, sir.
All right, so there are more electrons. So the electron cloud is larger, okay, and that it gets more easily distorted. All right, who was that? Who answered? I think it's the random movements. Sir, what makes the electrons become distorted? Remember that the electrons have random motions. Okay, random motions. So if you place them together with another, the nucleus of that other atom who may attract the electron cloud, okay, of atom B. Okay, so that's what makes the electron cloud a little distorted. Okay? And then the randomness also of the movement of electrons. All right. So halogens and noble gases boiling point increase with molar mass. Okay. So in terms of the relative magnitudes of forces in molecular compounds, okay. Again, this is still molecular compounds, huh? We are saying that covalent bonds are the strongest. So it's the attraction between the atoms in a molecule. Okay, it's where energy was stored. Now, in between molecules, the strongest one is hydrogen bonding, and then you have dipole-dipole interactions and London dispersion forces. So the LDFs are the weakest. Okay, so whenever you see kanang molecules, all of these may be present. All of these may be present. And then it kind of stabilizes their structure, okay? Especially, for example, on biological systems. So I hope you are familiar with the phospholipid bilayer. So this is the one uh, that is present in cell membranes, the ones that protect the other organelles, okay, from outsiders. So you actually have a phospholipid bilayer. So this is the fluid mosaic model, okay. Biochemists use this to explain the entry and the exit of materials into and outside the cell. So they're saying that the cell membrane is made up of the phospholipid bilayer. So when you say phospholipid, it is composed of a molecule having a phosphate end. Okay, this is your phosphate, which is negatively charged. Okay, you just don't see all the dots there. It has been omitted for simplicity's sake. And then you have glycerol, okay, a special type of compound also. And then you have here your fatty acids, okay, either saturated or unsaturated, okay. But what is significant here is that this line, okay, or your fatty acids are hydrophobic, meaning they are not soluble in water. They fear water. They do not mix with water. Hydrophobic. And why is that? That's because they are primarily nonpolar. All right? This end here is nonpolar. Now, the hydrophilic head, hydro meaning water, philic, philia, that means attracted to or love for, or water loving head is because of this ion. And this is the polar part of the molecule. It has a negative end. Okay, so take note that your phospholipid has a negative end, okay, or a polar end and a non-polar end. So you have a hydrophobic tail and a hydrophilic head. All right. So what happens here is they will arrange themselves, the phospholipid molecules will arrange themselves such that the polar ends will be coming together, okay, will be coming together as and the nonpolar ends will be going together. All right. So you expect here that you have your London dispersion force in this area. Okay. And then we call this now your phospholipid liposome. Right. So where is this significant? Why is this significant? Again, there is a positive end or a polar end and a non-polar end. So this is basically for generally the structure for most cell membranes, okay? That of humans and even that of viruses, all right? But it's not all that there is, by the way, in the cell membrane. Huh? There are also, for example, cholesterol, gangliosides, ribocytes, and other compounds. But just so you get the general structure. So here is a 3D model depicting how the phospholipid bilayer will arrange itself. So you notice that the polar end, okay, will be facing towards the aqueous environment. So imagine that there will be water here inside and outside. All right. So there is a nonpolar end here that stays away from water, and there is an inner aqueous compartment, okay, where you can also find all other cell organelles. Okay, and you have hydrophilic surfaces and hydrophobic tails. So what happens now is these are used to enclose the different parts of the cell. Okay, it can, for example, it can enclose DNA, it can enclose RNA. Okay, remember that viruses, specifically coronaviruses, they are primarily RNA enclosed in a layer, okay, in a protein layer, okay, or in a layer with spike proteins. The spikes there are actually proteins, that the one I've shown a while ago, but they just resemble crowns. All right. So these are now your the crowns or the spike proteins, and we know that this is enclosed in the oily lipids or the bilayer, all right, which has a positive and a negative end. So if you introduce a certain molecule, let's say for example that of soap, okay, A soap molecule has a head as a polar end, just like a while ago, has a part that is polar, that will bond with water, and there is an end that will not bond with water, but will bond with the oils, okay, or will with the phospholipids, okay. So if you introduce this one, if you wash your hands with water, okay, you are actually making these two parts interact. You are making either the polar bond or the polar part interact with the polar part of the cell, and the nonpolar part of soap interacts with the nonpolar part of the cell. All right. So here, when using soap and water to wash the hand, the soap molecules will have a head that bonds with water. So this area here will bond with H2O, and a tail that bonds with the oily lipids or the phospholipid bilayer. Okay, so the tails of the soap molecules will attempt to bond with oily protective barrier of the virus. Okay, so soap has a non-polar bond. It will be integrated into the non-polar, and also in doing so, they are breaking the arrangement. They are breaking the protective layer. Okay? They are breaking the protective bilayer and thereby releasing the RNA or in the coronaviruses is RNA man, no? So RNA, so they will release the RNA before it gets to our cells. Okay, before our cells kind of binds to this as to the spike proteins. So what we are practically doing if we are washing our hands or our skin with soap is that we are breaking down the virus. Okay, so the soap molecules surround the fragments, encapsulating them before being washed away with water. So take note that the polar ends are attracted to water. They will go with the water down the drain. All right. Now, you might have encountered this and then might have considered using it in your PPT or your inner performance task. Okay, so another point to look into is how effective are alcohols or hand sanitizers. Okay, uh, are they viable replacements for soap? Okay, and then if you are using soap, which kind of soap are you using? So those are possible points for study. All right. So I'll be sending out videos, supplementary videos. You view them at your own pace. Okay, you do not need to sit down and then view the entire lecture because it's actually a conference in a particular university, and then it kind of encapsulates all the lessons that we have. Okay, and then I hope that it will be able to help you in your performance task. Okay, I'll give you time for your performance task on Thursday. All right. Now, for tomorrow, you will have this experiment on the properties of ionic and covalent compounds. All the instructions are there, and then no need for us to meet. The link is present in the assignment, which will be posted tomorrow. Said okay. So, do we have questions? So we're able to do this already, and then I leave it up to you to delve more and dig in more on how the properties of compounds are based on the forces, both inter and intramolecular forces. Right? So, do we have questions? You still there?
Yes, sir.
Okay, so if there are no more questions, that practically ends module one. So tomorrow, let's the last virtual lab for module one, and then Wednesday will be tests. So prepare if you need to review. The videos are present in the YouTube channel. Okay, what do we do with the performance task? You are going to come up with a position paper. Uh, you are going to come up with a position paper and propose new ways to improve a certain health practice. Okay, so this is, for example, in diba in the springboard, 0 point something, we actually gathered data, policies or practices. Then you have to choose the chemical compound present there and then characterize it. Okay, so in the performance task for Gen Chem, you are going to come up as a group with a position paper detailing the merits, okay, the scientific basis of that particular practice, okay, whether it is scientifically sound or not. Or so, for example, the one I've shown, washing of hands, where you use a particular soap, okay, a certain soap, and then you claim that this will be more this is more effective than the other soaps. Or there you might have heard about studies on the virgin coconut oil being used to treat COVID. Okay, and you want to figure out where is the merit in that. Okay, or you want to look into toob. What is in toob? What is in steam inhalation? Diba? But it's actually being debunked now. Okay, so things like that. And then after that one, you suggest, you will propose, okay, this is creation now. This, you will propose a new way of improving that particular practice. Okay. Now, since this is an integrated performance task, it's only the content that is the concern of Gen Chem. Okay, so meaning you can add more. So, for example, if you want to add policies, if you want to add, you maybe you suggest the placement of hand washing stations with this amount of soap, that would be good. That is one good example. Okay, you suggest to a particular establishment that you will be using, so things like that. Since this is an integrated performance task, so DRRR has something to look into also, as well as oral com. Because after the position paper, you are actually going to present the summary of your findings and of your proposals, of your suggestions in a video, okay, in a vlog, okay, and that is where oral com comes in. Okay. Now I'm still waiting for the cluster head of Oralcom to finalize na the rubrics. Since again we have a new grading scheme. So once that is ready, I will present the whole details to you. All right. But I understand you are already being grouped. Okay, you have your groupings already, and then you are assigned the special channels for your teams. Okay, so I'll be doing the same thing. That will be on Thursday, and to give you time as well. All right.
Sir, is the position paper separate from the capstone or is it just a part of it?
It's a part of it. It's
But
a
is it graded separately?
I will be grading the position paper.
So but the capstone itself doesn't have an overall grade.
It will. No. The capstone has its rubrics. No, you have a certain rubric. And then, for example, Gen Chem, here are the competencies, and then again, competency-based naman ka, and then DRRR, and then oral com. So each part, each competency will be graded by your respective teacher. Okay? So that means whatever competency is there is present, which concerns our subject, we will be the ones to grade. All right?
So is like the average of the three competencies the overall grade for capstone?
And that's what we are waiting for, the final instructions, because I don't think there will be an average grade for the whole, because again we are dealing with if there is an average grade, it's like having points man good. Yeah,
Oh,
so
oh, yeah,
that's
fair point.
competency.
Fair point.
So again, we are not using the points naman. So based on competency lang. It's just that there are just two main tasks, two big tasks, and then three subjects are grading na per
Sige, sir.
competency.
Thank you, sir.
Okay? So if there are no more questions, you can spend the rest of the time taking wait